Good morning, students. So for today, we will discuss about simple and compound machine efficiency through translational and rotational motion. So this is our third lesson. So for our learning targets, at the end of the class, the students can first identify examples of compound machines used in home, schools, transportation, and industries. Second, differentiate machines according to structure, function, and efficiency. Third, explain how machine efficiency influences performance and energy consumption in daily applications through problem solving. And lastly, propose practical and achievable strategies for reducing energy loss and improving energy efficiency. And for our essential question that you have to answer in your notebook, how can understanding simple and compound machines help us accomplish everyday tasks more efficiently while promoting safety and responsible use of technology? So for our short activity, so kindly write your answer in your notebook. What machines do you use every day? So kindly list down all the machines you encountered every day. And how do they make your work easier? So again, write your answers in your notebook. So, what is a machine? Now, let's understand what is a machine. A machine is a device that makes work easier by modifying force or motion. So, this means that machines help us perform tasks more efficiently by reducing the amount of effort needed or by changing the way we apply force. So, machines can help us in different ways. They can multiply force, allowing us to lift or move heavy objects more easily. They can also change the direction of force. For example, when you pull down on a rope attached to a pulley, the object moves upward. So some machines can even increase speed, helping us complete tasks more quickly. Another important concept is that all machines rely on motion. So they either use linear motion, which is movement in a straight line, or rotational motion, which is movement around a fixed point or axis. Many machines use one type of motion while others combine both. And because of these functions, machines save effort and time. So they allow us to accomplish tasks that would otherwise be difficult, time consuming, or even impossible to do by hand. So this is why machines are essential in our homes, schools, transportation, systems, industries, and many other areas of daily life. Now that we know a machine is a device that makes work easier by modifying force or motion, let's see how machines use motion in everyday life. So first we have a bicycle. So what parts of the bicycles are moving? Okay, so we have wheels, pedals, and gears spin, which is under rotational motion. And as they rotate, the bicycle moves forward in a straight line, and this is translational motion. Second one is the wind turbine. What makes the blades move? So that's correct, wind. Okay? So the wind causes the blades to rotate. The rotational motion turns a generator producing an electrical energy. And for the third one, we have the crane and lifting machines. So a crane uses a rotating pulley to lift heavy objects. While the pulley rotates, the load moves up and down in a straight line, showing translational motion. And lastly, we have the car engine. Inside the car engine, the pistons move up and down using a translational motion. So this motion turns the crankshaft, creating rotational motions that powers the wheels. And what do all these machines have in common? They all use motion. Okay? So machines use rotational motion, translational motion, or both to make work easier and more efficient. So this is the same principle behind the simple machines we will study next. Now that we know machines make work easier, so let's take 1 minute to observe these two pictures carefully. So just look at their design, how they might work, and what you notice. So, what do you notice about the first machine? How about the second machine? And what difference can you observe? Okay. Now, even though these machines look different, they were designed to accomplish the same task. However, they do it in different ways. Now, let's think more deeply. How do old machines use motion to perform work? And second, how do modern machines improve efficiency? So kindly answer this in your notebook as well. Again, for first or number one, how do old machines use motion to perform work? And how do modern machines improve efficiency? We've seen that both old and modern machines perform the same task. So why are modern machines better? So first, modern machines have less friction. So this means fewer parts rub against each other, so they move more smoothly and waste less energy. Second, they are made with better materials. Stronger and lighter materials make machines more durable, safer, and longer lasting. And finally, modern machines have improved motion conversion. They can transfer or change motion more efficiently. For example, converting rotational motion into translational motion with less energy loss. And because of these improvements, modern machines work faster, require less effort, and use energy more efficiently. So, in fact, the foundation of every complex machine is the simple machine. Now let's begin by exploring the six types of simple machines and how each one makes work easier. So what is a simple machine? So it is a basic design to make work easier. So each simple machine has a specific function. Some help lift heavy objects, some change the direction of force, while others reduce the effort needed to move a load. Although they are simple, they are very important because they are building blocks of complex machines. So, in fact, many of the machines we use every day, such as the bicycles, cranes, cars, and wind turbines, are made by combining two or more simple machines. Now, let's explore the six types of simple machines and discover how each one makes work easier. First one is a lever. It is a simple machine consisting of a plank or a beam that can rotate freely about a fixed point. It is used for moving, lifting, or propelling objects. Now, who invented the lever? So, if you know who is Archimedes, so he is a Greek mathematician who was the first one to develop the lever principles in 260 BC. And we have different parts of a lever. So a lever system consists of four parts. We have beam, a plank made out of wood or metal, fulcrum, the pivot point about which the beam rests and moves freely. Since the beam can move freely, the fulcrum is also known as the lever's turning point. We also have load, the object on the beam that the lever tries to move or lift, and the effort, the force applied to lift or move the object, resulting in work. So here are the parts of a lever. Now, how does a lever work? So a lever works by reducing the force applied to move a heavy object. A beam is placed on a fulcrum and an object is positioned on the beam. A force is applied somewhere on the beam, and the beam pivots around the fulcrum and lifts the object. The relative positions of the fulcrum and the load are adjusted to minimize the applied force. So the beam rotates about the pivot point. A torque is necessary to rotate the beam and lift the object. So the basic principle is that the applied torque manifests at the load. Okay? Now, for mechanical advantage, it shows how much a lever multiplies the applied force. So it depends on the positions of the fulcrum, effort, and load. So for our formula, we have MA, or the mechanical advantage, is equivalent to load divided by effort. Okay. So the key idea of this is longer effort arm is equivalent to a greater mechanical advantage. And if we have a greater mechanical advantage, there will be a less effort needed. So it is inversely proportional. Okay. And then placing the fulcrum closer to the load makes lifting easier. Okay, so if you observe po on, for example, you hold a broom, no, you use a broomstick, no, so saan po ba kayo mahawak dun sa dulo ng broomstick or dun sa gitna or banda po sa malapit sa load, no? So we often use to hold it nearer to the load, okay, so that uh, we can use the broomstick easier. Okay. Now, another example of this is using a crowbar to lift a heavy rock. So place the fulcrum, a small block or stone close to the rock, push down on the long end of the crowbar, and the long effort arm creates a greater mechanical advantage, allowing you to lift the heavy rock with less force. Okay? So some applications we can observe, for example po, we have the scissors, battle opener, tongs, fishing rod, hammer, and wheel barrow. Second one, we have the wheel and axle. So it is a large wheel connected to a smaller axle, converts rotational motion into translational, and it is used in vehicles and machinery for easier movement. Now, who invented the wheel and axle? So, archaeological evidence shows that the first wheel and axle existed in Mesopotamia during the Bronze Age around 3500 BC. Now, how does a wheel and axle work? So, wheel and axle works through rotational motion. So, applying a force to the wheel and axle creates a torque, causing both parts to rotate together. The wheel and axle rotate at the same speed, but the larger wheel covers a greater distance. So, a larger wheel helps reduce the effort needed to move or lift a load. So, some real life examples of a wheel and axle, we have a steering wheel, wherein it turning the large steering wheel rotates the smaller steering shaft to change the direction of the car. We also have the doorknob. Turning the knob or the wheel rotates the spindle or the axle to open the door. Okay, and the last one is the water well, wherein turning the wheel winds the rope around the axle to lift a bucket of water. Now, what's the mechanical advantage or MA of a wheel and axle? Okay, so it depends on the size of the wheel and the size of the axle. Okay, so we have the EMA is equivalent to the wheel radius, the capital R, over the smaller or the radius of the axle. Okay, so capital R is the radius of the wheel over the radius of the axle. So the key idea is a larger wheel provides a greater mechanical advantage. The bigger the wheel compared to the axle, the less force is needed to move or lift a load. Okay, so again, here are the examples of mechanical advantage of wheel and axle. So some examples, we have the bicycle, car tires, Ferris wheel, electric fan, analog clock, and winch. Third one is the inclined plane. So this is the flat surface set at an angle used to raise or lower objects. So it reduces the force needed by increasing the distance of movement. So how does an inclined plane work? So an inclined plane is a sloping surface that makes lifting or moving objects easier. So it reduces the force needed to lift an object by increasing the distance traveled. It's instead of lifting an object straight up, you move it along the slope. And this makes it easier to overcome the gravity. Now, the mechanical advantage of an inclined plane, it reduces the effort needed to lift an object. So it depends on the length and height of the ramp. So for the formula, we have the EMA, or the ideal mechanical advantage, is equivalent to the length of ramp divided by height of ramp. Okay? So the key idea is a longer ramp requires a less force to move an object. And then if there is a less force, there will be a longer distance traveled. Okay? So some example po of an inclined plane. So there is an applied force using the ramp, less force needed. There is a longer distance. So lifting straight up, more force needed, shorter distance. So that's the advantage of using an inclined plane. Okay, next we have pulley. So a wheel with a rope or cable used to lift loads. So it changes the direction of force or reduces effort. It is used in a flagpole, crane, and elevator system. Our Greek mathematician and physicist Archimedes is credited to have invented the pulley in the 3rd century of BC. Now, how does pulley work? A pulley helps lift heavy objects more easily. When you pull the rope, the wheel turns and lifts the load. And the groove keeps the rope from slipping off the wheel. More pulleys mean less force is needed to lift the load. So heavier objects still require more work to lift. So what's the mechanical advantage of a pulley? So it shows how much a pulley reduces the effort needed to lift a load. So it depends on the number of supporting rope segments, or what we call loops. Okay? So the formula is load divided by effort, or the number of supporting rope segments. So the key idea is more rope loops is equivalent to greater mechanical advantage and less effort needed. So with more loops, you must pull the rope a longer distance to lift the load. So for an example is the construction crane. So this is the construction crane. A crane with multiple pulleys can lift heavy steel beams using less force. So workers pull more rope, but the heavy load becomes easier to lift. So this is the technique now that they use. Okay, they apply more more loops. So rope loops is equivalent to a higher ideal mechanical advantage, or the EMA, and less effort. Okay. Next is the screw. A screw is simply an inclined plane wrapped around a cylinder. When you turn a screw, it uses rotational motion. As it rotates, it moves forward or backward in a straight line. So converting rotational motion into a linear motion. So this allows screws to hold materials together tightly or move objects with a greater force. So some common examples of screws includes bolts and screws, jar lids, and drill bits. So remember, turning a screw creates forward movement, making fastening and lifting tasks easier. And lastly, we have the wedge. A wedge is a double inclined plane that is used to split, cut, or separate materials. When you apply force to the wide end of a wedge, it converts that force into outward forces at its sharp edges. So this makes cutting or splitting much easier. So common examples of wedge includes a knife, an axe, and a chisel. So remember, a wedge uses its sharp edge to concentrate force, making it easier to cut or split the materials. Now, we already identified the six types of simple machine, so let's apply this. So identify the type of simple machine for each object. Write your answer in your notebook. We will check this next meeting. So number one asks, which among the six simple machines, okay, we can consider no the axe. Second, doorknob. Third, ladder. Four, jar lid. Fifth, flagpole. Six, scissors. And seven is wheelbarrow. You can answer more than one simple machine. Okay. So now that's all for our part 1 lesson of a simple and compound machine. So next meeting we will learn more about the compound machines and uh, how efficient, okay, the use of a simple and compound machine. Okay? And don't forget to answer our essential question. Thank you so much for listening.